When we finished class on Saturday, we had a few extra topics to go through, so I'd like to finish those off in the next short video here. And I'd like to start off with picking up at the Coriolis Force as just a quick review before we move forward with the rest of the topics. So again, as a quick reminder, the Coriolis Force is an apparent deflection of an object due to the rotation of the Earth below it. In the northern hemisphere, that deflection is towards the right, and in the southern hemisphere, that deflection will be towards the left. If your wind speeds are stronger, you're going to have a greater deflection, and likewise, the further north you go towards the North Pole or the South Pole, that force or the apparent deflection is also greater. There is no Coriolis force in effect at the equator. Everything flows in a straight line. So from this point, we went on and we did a quick demonstration about how the Coriolis force works by using the example of two persons sitting on a merry-go-round tossing a ball back and forth to each other. While the person tosses the ball, appears to throw the ball directly at the receiver is moving away from the ball, and from above it looks like the ball is curving towards the right. This diagram from your book on page 213 shows that the higher the latitude goes, the stronger the Coriolis force gets, and also the higher your wind speed is, the stronger the Coriolis force gets. This diagram, if you recall, discussed what happens to an airplane who wants to fly across the longitude lines. The further north in latitude that the airplane is going, the harder it is to fly in a straight line. The Coriolis force makes the aircraft appear to want to deflect to the right and would deviate a large distance from the path that they actually want to take. Now compare the farthest north aircraft path to that on the equator, and you'll see what we're talking about when we say that the equator has no Coriolis force in effect, vice having a very strong Coriolis force in effect in the northern latitudes. This video that we watched, if you recall, was a YouTube video, once again demonstrating the Coriolis effect with the two gentlemen on the merry-go-round tossing a ball back and forth to each other. Now when we put this in terms of how an air parcel moves, we see that the air parcel moves from high pressure towards low pressure using the laws governing the pressure gradient force. Remember, air moves from high to low. So as the air parcel starts to move from high to low, as it picks up speed, and especially if it's going towards the north, towards a higher latitude, the Coriolis force tries to balance out the pressure gradient force. Once the pressure gradient force and Coriolis force are balanced out, the winds are in geostrophic balance. And at that point we call this the geostrophic wind. The geostrophic winds are impacted by the Earth turning, which would be the Coriolis force. Another characteristic of the geostrophic wind is they travel parallel to the isobars. And if you recall, an isobar is a line of constant pressure. The spacings of the isobars is significant. The closer the isobars are together, that's an indicator of faster wind speeds compared to when the isobars are spread further apart. There's a mathematical equation that governs the geostrophic wind, and that's listed here and described further in your book. If you read through the special topic on the geostrophic wind, you can learn more about this. In this course here, you won't be doing any significant mathematical calculation of the geostrophic wind using this formula. A couple other examples of how this works. The diagram to the left, something you may have experienced in real life, where you have a large body of water that starts flowing into a narrow body of water. We see that the water speeds up in velocity as it gets through this constriction. Very similar thing happens with wind speeds as they start moving into areas where the pressure gradient is a lot stronger. As you can see here, the pressure gradient force and the Coriolis force is balanced out as indicated by the vectors here. They're both of the same length in opposite directions. But as they move closer to point number 2, where the isobars are closer together, we see that the length of the pressure gradient force and Coriolis force vectors is longer, and that's an indicator of the force increasing. Consequently, you see that the wind speed vector here, this little purple line, is short, and as it goes in through the constriction, the speed gets faster. Once again, this is demonstrating the geostrophic winds, the relationship between geostrophic winds and the isobar spacing. The closer together the isobars, the faster the wind speed when they're in geostrophic balance. And the direction doesn't necessarily have to be in a straight line. In geostrophic winds, the winds continue to follow the parallel to the isobars as long as we're flowing in the right direction as we go around our low pressure systems and going around high pressure systems in a clockwise fashion. We see the isobars laid out in the diagram on the left and the associated wind vectors as they flow parallel to those isobars. Now those were definite diagrams. We're talking about winds at the surface. The gradient winds aloft or above the friction layer of the Earth operate in very much the same way, and we have some terminology that we wanted to use. Winds that are flowing in a counterclockwise fashion we call cyclonic, and winds that flow in a clockwise fashion are called anticyclonic. Those gradient winds will be parallel to the curved isobars or iso heights in those winds aloft. And down near the equator, because we don't have Coriolis force in effect, we use the term that it's cyclostrophic. So we can estimate the wind flow aloft by using satellites, for example, maybe aircraft observations. And we can take a look at those, plot them on a chart, and graph out exactly how the upper level winds are flowing. The winds will flow parallel to the contour lines that we talked about earlier in the class, the isoheight contour lines. And generally, in the northern hemisphere, those winds flow from west to east. Additionally, the heights on those upper level charts decrease from north to south. And through the week in the announcement section, I'll put up some examples of some upper level charts, and we'll talk about them at the beginning of each of our classes through the end of the term. Now, there's one force we didn't talk about at the surface, and I'd like to go back down to that level for a second, and that's the effect of friction. Friction slows down the wind speed, and if you remember what happens with the Coriolis force, the slower your wind speed, the lower your Coriolis force is. So while your pressure gradient force is pushing your wind to want to go a certain speed, friction is pulling it back slightly, and the Coriolis effect is also not able to get in balance with the pressure gradient force. Because this relationship of the vectors is not completely in balance, the winds actually are very hard at the surface to stay parallel to the isobars. They're actually slightly offset by about 30 degrees blowing into the low pressure area. This whole discussion here is called the Balogh Law. Once again, looking at vectors of how this works, in a cyclonic flow system to the left, we have our winds flowing parallel to the iso heights, where my pressure gradient force blowing into the low is balanced slightly by my Coriolis force. High pressure flows anticyclonically or clockwise around the high pressure system, and the winds are blowing away from it, blowing out of the high pressure system, and the Coriolis force and pressure gradient force here again are balanced as long as there's no friction acting on it. We can see this rotation of the counterclockwise or cyclonic flow around a low pressure system from satellites when they're animated. In the southern hemisphere, these low pressure systems rotate in the opposite direction. So in the northern hemisphere, they're counterclockwise. In the southern hemisphere, low pressure systems are flowing clockwise, and that's because the Coriolis force is deflecting that wind towards the left, towards the equator, towards the right, as we do in the northern hemisphere. This is what one of those upper air charts would look like, and again, I'll use more examples of this through the week. These wind barbs indicate the direction of flow, and the little flags on these indicate the speed, and you have a decoder chart over here to the right. But notice they all flow parallel to the contour lines across the United States. And notice that we have these little ridges and troughs associated with this, and I used the analogy in class the other day of a topographic map. This is the 500 millibar chart that we're looking at here. Every pressure on this chart equals 500 millibars, except you're measuring the height above ground that 500 millibars is being recorded at. So we're looking at the terrain of the 500 millibar surface. Where I have a ridge, I have warm air built up underneath the 500 millibar surface. Where I have a trough, I have cooler air or lower heights underneath the 500 millibar surface. If I try to stack include the friction in here at the surface, what I see is I have the pressure gradient force flowing from high to low. I have the Coriolis force slightly offset from my friction, and my actual surface wind speed, like I said, is tipped towards the contours by about 30 degrees. The same holds true as I look where my low pressure system, the winds funnel into the center of the low pressure system at the surface, and winds aloft are flowing in a cyclonic curvature here. Now, this is an open curve. If I were to complete the curve all the way around, this would be a counterclockwise circulation completely around the low. Here's a high pressure system at the surface flowing clockwise. Likewise, above at the upper levels, it is flowing in an anticyclonic ridge. If I complete the circle around that ridge line, it would actually be a clockwise circle. In the southern hemisphere, as I've mentioned earlier, the pattern is reversed. This is what a surface chart would look like in the southern hemisphere, again, where the winds around the lows are going clockwise and counterclockwise around the high. Now, we talked about how do I get air to rise in the earlier week. Week 5, I believe, week 4 talked about that, I'm sorry. One of the ways to do that was to have winds converging together. So this is what we're going to talk about here. So the first thing you got to do is figure out where the low pressure system is, and here's a general rule of thumb. If you put your wind put the wind to your back, raise your arms out to your side. With the wind at your back of the northern hemisphere, the low pressure will be to your left. If you want to be totally accurate, you need to turn yourself slightly 30 degrees off center to account for friction. So once you figure out where the low pressure area is, we talked about an area of convergence causing air to rise. If I have air piling up in one area, air can't go down. The only place it can do is forced upward into the air. So that's what we call converge. Air converges on a single point, and the only place it can go is upwards. So the rising air gets to a point where it doesn't go any further, and it starts to diverge. High pressure, if you remember at the surface, is evacuating air away towards low pressure, and I end up with this area where I need to fill air in. So what happens above the high pressure? Air sinks. Now, if you remember what happens with sinking air from previous chapters, sinking air has a tendency to compress itself and to also warm up. And over the top of high pressure areas, this is why you don't see a lot of clouds. This is also governed by a mathematical equation that we won't work with much here in the course. The book has a decent discussion on it, but it's called the hydrostatic equation. And this is how you can judge the changes in heights with different elements by looking at the change in pressure. So we're at the end of the chapter. We took a look at differences in air pressure and what causes air to move, because remember, air moving is wind, and it's a result of difference in pressure between 2 points. We looked at how air pressure is represented on surface charts and upper level charts, the 4 factors that affect the horizontal movement of air. We looked at the difference between a geostrophic wind and a gradient wind. Remember, geostrophic wind flows parallel to the isobars or the contour lines. Gradient wind is flowing from high pressure towards low pressure, turns with Coriolis force balance, taking friction into account, and then as the contour lines get closer to each other, they speed up. As they get farther apart from each other, they slow down. Okay, if you have any questions on this, please feel free to send me an email or give me a call. I'll be more than happy to explain anything further.